Well, thank you for attending the webinar this morning. As Srinivas says, I've been using Nastran for a long time, 10 years in the aero defense industry, past 20 plus in the automotive and just general engineering. I've seen our compute environment change drastically over these years. From the CDC, IBM, UNIVAC era, when the PC was released by IBM, the XT, AT, and now laptop and tablets, and the other associated things that go along with it, the automation process of CAE practices. So I want to go through a bit of history because there are students and others on here who probably haven't seen what I have over the years. And I want to say that, my view is anything past displacement calculation and CAE is post-processing. Stresses, of course, are done inside the FEM codes, but what you do afterwards depends on when you start in engineering. Manual hand calculations. Anyone who's in aerospace probably knows of Bruin's handbook and the calculations that to be done for margins of safety. If you're in just general engineering, there's a lot of handbooks. Rourke's is one that everyone probably remembers for stress and strain. So the first step in automation is essentially these handbooks so that everyone's using the same equation to get the same answer, and that's the important part. Which then leads to, well, if you're doing these engineering calculations, I remember that, the first time you through it, it's kind of interesting, then it becomes kind of boring, which means it's error prone. There's a lot of physical time involved with it because we always had a checker to sign off on that, and that's probably still around in some areas. Someone check your hand calculations, make sure you're doing the right thing. Finite elements, of course, produce volumes of information, and you're not about to do a stress calculation for every element, although you would like to, because that would eliminate errors. So here's our first step in automation is someone writes a program, and I've written them, maybe a few of you have too, to run this stuff. Now we've got a process that we're going to do, and it becomes standard within the company. Everyone accepts it. Everyone's doing it. We can do these on programmable calculators. You've got private commercial software where some might remember TK Solver. It's still around, where they had brought in formulas from Rourke's handbook so that you could just go through an interface and calculate things. So enough of that. Now the CAE process, whether you're in automotive or aerospace, it's pretty much defined, and it's become big, and everyone follows it so that anyone can sit down and do this. Every company has their own CAE process. If you're using all MSC products, you go through a loop of some sort, whether you start out with CAD. You could bring it into our Apex product and clean up and mesh it, then send that out either to one of our FEM solvers, which communicates with Actran or Atoms possibly, or you can go straight and just do your FEM analysis and then use the post-process in one of the GUIs, Actran, SimExpert, MedTat. Apex can do that. VI is for Actran, but there is a defined process that you do here. You go through this loop and you repeat it over and over again. And in some cases, you have your own code that you insert into this. One of the big things that you don't want to do, and this has become so important today, is you don't want to break it. Because if you break it, you increase time and cost. That raises management's eyes to see what's going on. Different results. They're not wrong, but they're different. So if you're going to replace some type of calculation in your process, you want to make sure that it fits in and doesn't cause any problems. I know this. Our salespeople know this, so we don't come to you with suggestions that will make your life miserable. That's not conducive. So if we want to improve things, whether it's a commercial CAE or yourself, you know you got to save physical wall time. That's engineering cost and computer time. And you got to fit in with little or no changes. Some changes, maybe you have to call out a different code to do something or a little bit of file format, but once it's done, it never has to change again. So we're going to talk about the fatigue step in CAE and how we can improve that time, shorten it down, and not break your process. So everyone has at least done at least one fatigue calculation somewhere in your career. You know, if you're a student, you do a simple SN curve lookup. You might use one of the equation Gerbers or Soderbergs. You'll do this a couple homework problems, maybe a test problem. You might even, you know, have a homework problem that considers the surface conditions or pre-stress. After that, it becomes more involved, and at that point, you want to start considering doing a code to do this. If you're going to look at multi-axial, spot welds, seam welds, or if you're looking at what they call EN analysis, which is strain-based, you have to do a computer calculation for this. Also, these FEM models, they build these, you know, these FEM models are so large that the volume of stress that comes out, almost mandatory that you have to filter things. So your general workflow is typically this. You'll run a finite element model. You'll produce a volume of FEA output. And you know, Nastran is very good, any FEM code is very good at producing lots of data for you. It'll typically be, you know, binary. For us, it's OP2. That's our format. Now you're going to have to translate that, which means someone's got to write a code to read that, whether it's the commercial fatigue code or you've written one because you have your own fatigue code that you've done. So you turn that into a very large file. If you go ASCII, things have expanded tremendously. You'll have to bring in your material properties. That usually doesn't change. That's pretty standard once you've got it set up. And then your cyclic load data. Again, those are usually standard and they don't change. Particularly if you're in a process, you don't change those things. You use standard stuff over and over again. Then you go and you do your fatigue calculation. You might have to write some type of translator to put the output in a format that a graphical interface could use and actually display as a fringe plot like we see here, and print it out and so on. But these fatigue codes are generally independent of your workflow. You're using someone from the outside, and you've got to insert it inside there. Now, in order to do that with non-Nastran, you know, fatigue type codes, we've got three ways of going about this. The first one is very typical. Shell script, whether it's a Unix type scripting or Python, whatever your favorite code, you know, coding translator is, you'll build that. It's usually an executable that runs after Nastran is completed. It's very, very common. Now you've got the cost of someone that has to maintain that and keep track of it. So IT departments don't like to do that. And you've got all the disk space that you've got to maintain, or open disk space for these large files that have to be dealt with. And then there's transfer costs and so on, depending on how big your models is, how big your, you know, what's your intranet set up at your company. Another way to do this, which makes it a little bit easier, is we've got a module inside Nastran called iShell, which pauses Nastran while a third party will execute and the Nastran starts up again. Problem is that when Nastran sits idle, because the batch program, for any batch program, it holds that memory and disk, eating that up. Well, that's a detriment. Also, you're not using the efficiency that we have inside Nastran for file and I/O handling. We're very, very good at doing this. We handle very large models, and we've been doing it for 30 years. The third way of doing this, and this has been a little more recent with some changes in the Nastran file management that we have, is compiling the executable library right within Nastran. This is relatively new, but the advantage here is that you're using the MSC Nastran file and I/O handling capabilities. Licensing becomes easier because it's embedded within our licensing system, so it becomes a feature. Or if you do this yourself, you don't have to license it, it's your own code. But also, it's the familiar Nastran data file to supply information. Over the years, this has just become a standard, the bulk data file, and it never changes from version to version. It gets improved with additions, but you know that it'll always be, upwards compatible. So what we've done is we've turned it into a DMAP library call, which is the Nastran scripting language, is DMAP. So it's fatigue solve, and we've had a long relationship with Ncode. So what it is the DTLIB that you see in Ncode's fatigue solver. And we call it out and we build all the files for them. We get it all set up. We're using the Nastran databases, Scratch, and the data management to maintain this information that goes inside there. And if you look in the installation, you'll see there's the Ncode libraries that we're calling and using. So Nastran's running, we're using the memory. We're not tying it up while it's sitting there idle. We give that over to the DTLIB and let it execute. So now what we've done is we've compressed things. Now when you run your finite model, and we support the three methods of doing fatigue analysis: statics, normal modes, and mode transient. All the fatigue material properties are in bulk data format, and we run the DTLIB right within Nastran. Your loads database does not change. We aren't going to make you turn that into anything different or unusual. We'll read the DAC file and the RPC as they are. So we're not going to cause any difficulties in that part of your process. And the fatigue output will, as I show you later on, you'll be pleased that it's basically the stuff that you are looking for. Not only our standard stuff, but some additional. So this one demo model that we've shown over the years, this is a Navistar cab for a truck. At that time, it's relatively small. Space requirements have dropped dramatically, as you see on the chart here. Anyone who's used what we call NEF, which is our embedded fatigue, has seen at least a 90% reduction in file storage. If you're running a simple model, like a keyhole, a standard one that everyone executes in their fatigue code to show that we do get the same answer, your CPU time will be about the same. But as your model sizes grow, and I know there are very large models out there, and it's the tendency of FEA is to build huge models, your CPU time starts to starts to drop. We're seeing 20 to 30% reduction in time, sometimes larger depending on the inefficiencies of the old method, where the fatigue solver is outside. So it's a lot simpler to do, which is great for your process. It's faster, smaller. It's also portable too. And once you have everything built, because it's a post-process, you have the data structure in there to launch fatigue. You can run it over and over again, and you don't have to touch it. So this model, at one time, it ran through MSC Fatigue, where we use the DTLIB solver inside Patran as the pre and post, but still we had these intermediate files. At that time, it took about 120 minutes to run all the way through. 191 individual files had to be processed and stored on the disk. When we moved this over to the embedded fatigue, we dropped our solution time to 25 minutes, Only 32 megabytes of disk space compared to 282,000 before that. Obviously, the results are the same. They have to, because we're using the same solver. And we only had 2 individual files to deal with, the input file and the other one being the results. So we've kept everything inside the Nastran Scratch database. Well, the good thing about this is that right now it would take 120 minutes. Well, that's, 2 cycles per day. Now we've dropped it to 8. This means if you're doing any type of MDO or DOE type analysis, the more you can do in one cycle during the day, and that's the goal, the faster that you can get to the optimized or what you're going to do with the MDO. This wheel carrier or steering knuckle, this one took 8 hours to do the fatigue results. I was told it's the multi-axial calculations which really sucked up the time. Well, we brought into NEF, it now takes 38 minutes. You see, depending on what you want to do in the fatigue, you can have some huge CPU time gains. Full car body. This is typical up here in Detroit. It'll be a Solution 112, the modal transient. And actually, this one's 4 million degrees of freedom. That's really rather small. But even at that size, you want to do fatigue filtering. That's standard capability in DTLIB, and we have that enabled inside NEF, where you'll, first step, of course, is to filter on element stresses and damage. Then you go through and you compress the time history, which is another filtering step. And then when the final results come out, you go back and do a complete fatigue analysis on the remaining elements. This type of filtering avoids a typical error of having to select a group of elements to process. But what if you pick the wrong group of elements and the one that's really critical hasn't been processed? Well, this type of fatigue filtering avoids that. Everything gets looked at. And now we can do this one in 2.5 hours. We've got it hooked up with our Solution 200. And this simple model, just an I-beam with some holes on it. We want to do a stress and a shape optimization. And in the past, before fatigue, if we ran this, you'd get 39% mass reduction, which is great. But if you ran a fatigue analysis post on that, you had failure at 10 to the 5th cycles. So now what you've done is you actually built a prototype and induced that cost, or you've had that cost now, the test failed, you have to go back again and include fatigue in the optimization. Well, when we do that within Nastran Sol 200, we get the I-beam shape in the lower right corner. You don't get as much mass reduction, but you get failure at 10 to the 8th cycles, which is what the criteria was. Here it's a shock tower. Unfortunately, it's been turned 90 degrees instead of pointing straight up, but all the shell thicknesses, because there's individual panels that make up these shock towers. Each one of them can be a design variable. And if we, of course, you want to minimize weight, but we'll include fatigue on this. So the summary on this one is, we knocked weight down, we got 24% reduction, and we brought life up from 0.7 to 0.8. And here's the individual thicknesses on those pieces that put that together. The next question is, well, to put those together, you have to use spot welds. And yes, we have the spot weld fatigue analysis inside NEF. The common modeling methods out there are bars or beams. There's the MSC C-weld element that we can handle. And there's another technique that uses the solid hex element with the rigid body element number 3 to connect it down to the patch. That way the little spot weld, which is that red nugget, does not have to be exactly on top of the grid point. Our weld element is the same way. With bars and beams, they have to be grid-to-grid connection, which puts a lot of restriction on that. So we could include, if we had spot welds, also as part of the fatigue analysis. And we can do seam welds. Seam welds are modeled as shell elements, quad 4s or equivalent. There's root elements, toe elements, and the yellow, which is the actual throat that you want to take a look at. So we can process these inside NEF. And these different types of seams can be modeled, those shell elements, and used inside the fatigue analysis that's inside Nastran. Output formats. Besides the normal OP2 punch file, we'll give you the ASCII universal file of the CSV. We will give you the HyperMesh HYP extension, if that's what you want to post-process in. The Design Life FER will come out. In fact, you can get every one of these output files all at the same time if you'd like. Our product, Pattrain, has complete pre- and post support, and our good friends over at ANSA also have complete pre- and post support for this fatigue input and output. So, by embedding the NEF inside Nastran, we're not going to break anyone's process. We're going to use the same DAC RCP files. It's all DTLIB fatigue options, nothing different, so you'll get the same answers. So we're going to reduce your data storage, definitely reduce wall clock time. You also get to use our SMP license for parallel support, which essentially gives you unlimited core access. Fatigue analysis on an element is essentially independent of each other, so each one of these cores, or what do you want to call them, math processors or CPUs, can process groups of elements individually. So it is like explicit code. It scales linearly with the number of cores. If you have just a few elements, you don't need to have 16 cores active. That's kind of a waste. But if you have a very large model and you want to take a look at every element, we really scale linearly with those elements and the number of cores. We've got the direct link to the Nastran optimizer. And if you're doing an MDO where you're using, let's say, Mode Frontier, and you have a separate Nastran and then fatigue analysis as two different inputs, we can now merge those into one. You only have one thing to execute, and it's faster, so your overall MDO will run much faster.